Hello friends, welcome back to edupediaword.com, your destination to free online education. In this video, we will learn how to prove the irrationality of the given irrational number. But first of all, let us learn a theorem. Friends, the theorem says if we have two numbers A and P such that P is a prime number and A is a positive integer, then if P divides A square, then P will also divides A. That is, if you have a number, say A as 15, then if another number, say 3 be P, then according to our theorem, if 3 divides 15 square, then 3 will also divide A, that is 15. Now let us learn how is it possible. First of all, the formal statement of this theorem, that is, let P be a prime number if P divides A square, then P divides A, where A is a positive integer. So, to prove this theorem and to understand this theorem also, let the prime factorization of A be written as P1 into P2 into P3 up to Pn. So by fundamental theorem of arithmetic, we know that this prime factorization is unique. Let this be equation 1. Since we need to involve A square also, so let us square this complete equation. That is, A square will be the square of this expression. Or P1 square into P2 square into P3 square up to Pn square. Now friends, since this is prime factorization, that is P1, P2 up to Pn are all primes. So this equation is also involving prime factorization. Therefore, when written in the increasing order, and let us say P1, P2, Pn, this be the increasing order of primes, so this becomes P1 into P1 into P2 into P2 into Pn into Pn. Now friends, if P divides A square, let P divides A square. Since P is a prime and the prime factorization of A square is this equation, that is, the prime involved are again P1, P2 up to Pn, which are the same prime factors involved in equation 1, but only their quantity has been doubled in equation 2. So since we have assumed that P divides A square and P is a prime, So it will mean that P is one among these values P1, P2 up to Pn. That is, P can be any value P1, P2 up to Pn, because prime factorization of a number is unique, and P can be any prime factor among that prime factorization expression. Now we have concluded that P can be any value from these set of values. So P can also be substituted here in this expression. That is, if P is P1, then A can be P into P2 up to Pn. If P is P2, then A can be P1 into P up to Pn. And we know that P can take only the values from these sets. So in any situation, either P is P1 or P2 or Pn, it can be substituted in this expression. So in other words, the prime factorization of A also include P as one of its factor. Now since P will be occurring in this prime factorization part, that is, A will be P into some product of the remaining terms from this expression. So it can again be seen as the case of Euclid's division lemma as A is equal to P into some value x, which is integer, plus 0. Thus we can say that P divides A. That is the given statement of the given theorem. So in this case, if 3 divides 15 square, then 3 divides 15 also. The prime factorization of 15 is 3 into 5. 15 square will be 3 into 3 into 5 into 5. We can see that 3 divides 15 square because 3 and 5 are the only prime factors involved in the 15 square, and we can see here that 3 also divides 15. Similarly, if we have some other number, say 14, and its square, then 14 can be written as 2 into 7 in prime factorization, whereas 14 square equals 2 into 7 whole square, that is 2 into 2 into 7 into 7. So 2 and 7 are the primes that divide 14 square. Thus 2 and 7 also divide 14. Now friends, we have discussed this theorem. Let us discuss how to prove the irrationality of the given irrational number. Friends, any real number can either be a rational number or it can be irrational number. The rational number is of the form A equal P by Q, where P and Q are coprimes. By coprimes we mean that P and Q are integers having no common factor, and Q is also not equal to 0. because if q is 0, then this term will become not determined or not defined. Whereas the numbers which don't satisfy this condition are known as irrational numbers. So, the under root of some numbers, like the prime numbers 2, 3, 5, 7, they don't exist or they cannot be expressed in the form p by q. That is, under root 2 can be only expressed as root 2 by 1. Similarly, all these numbers. P or numerator here is not an integer. Whereas we also have some numbers in squares like under root 16 and under root 25, which can be expressed by plus minus 4 plus minus 5, that is, one number will be 4 over 1, or here the one number of this will be 5 over 1, other will also be minus 5 by 1. Clearly p and q, or the numerator and denominators, are integers and they are having no common factors. No doubt 1 can be one of the common factor, but no other common factor. Similarly is the case with this number. We can also have numbers like 12 by 24. Clearly their common factor is 12, but it can also be expressed as 1 by 2. Now here we don't have any common factor between numerator and denominator, and numerator and denominator are integers. Thus, in the simplest form, 12 by 24 can be expressed as this form. So again, a rational number. Now let us discuss how to prove that these numbers are irrational numbers, whereas we know that these numbers are rational numbers. Friends, so we need to prove say under root 7 is an irrational number. Friends, to prove this statement, let us start with the opposite of this statement. That is, let under root 7 is a rational. Now since it is a rational, it can be expressed in this form. That is, under root 7 is equal to p by q, where p and q are coprimes or integers and q not equal to 0. For these integers, they have no common factor. Friends, remember, since we have assumed that under root 7 is a rational number, only then we are able to conclude this second part. If somehow it is an irrational number, then this statement is not possible. Now friends, let us label this equation as 1 and squaring both the sides of equation 1. We will get under root 7 square equals p by q whole square, or 7 equals p square over q square, which will give us 7q square equals p square. Let this be equation 2. Also from here we can conclude that if we again take the under root of this statement or simply modify this statement 1 from both or any of the statement, we can conclude that under root 7q is p, or p is under root 7q. Now friends, what does this equation signifies? P square equals 7q square. That is, if we see it as a case of Euclid's division lemma with remainder 0, then we can say that 7 divides p square, and 7 is a prime. So we can say by our theorem, if p is a prime and a is a positive integer, if p divides a square, then p divides a. Thus, we can say that 7 divides p. Now, since 7 divides p, which can further be modified as p equals 7m, because taking 7 as divisor, m will be some quotient. Now, here we have concluded that p is under root 7q, and here p as 7m. So from these equations 3 and 4, under root 7q equals 7m. Again, let us square this equation. We will get under root 7q whole square equals 7m whole square. That is, 7q square equals 49m square, or q square equals 7m square on taking 7 common. That is, q is divisible by 7, or 7 divides q square. That is, 7 divides q by our theorem, because 7 is a prime. Friends, from these two conclusions, 7 divides p and 7 divides q. That is, 7 is a factor common to p and q. But if under root 7 is a rational number, which we have assumed, then p and q will not have any common factor if under root 7 is written in its simplest form in this fraction. But we have concluded by taking under root 7 as a rational number that 7 is a factor common to p and q. So our assumption is totally wrong. That is, under root 7 is not a rational number. Now if it is not a rational number, then Since under root 7 is a real number, it will be irrational number, because a real number is either a rational or an irrational. Therefore, under root 7 is an irrational number. Similarly, we can prove the root of other primes like under root 2, under root 3, under root 5 are also irrational numbers. Now, sometimes we can be asked to prove irrationality of some more numbers like 4 minus 2 root 7 is an irrational number. Friends, to prove this statement, let us again first assume that this number 4 minus 2 root 7 is a rational number. Therefore, we can say that 4 minus 2 root 7 can be expressed as p by q, where p and q are integers having no common factor, and q is also not equal to 0. So we can modify this equation 1 as 4 minus p by q equals 2 root 7, or under root 7 equals 4 minus p by q divided by 2. That is, under root 7 equals 2 minus p by 2q, or 2q, and in the numerator after taking LCM as 4q minus p. Clearly this is a rational number, that is 2 by 1. 2 and 1 are co-primes. Similarly, p and q, we have assumed them as having no common factors on account of the complete number as a rational number. So if denominator only is multiplied by 2, again this will be a rational number. Now difference of these two terms will therefore be again a rational number. But previously we have just proved that under root 7 is an irrational number. Friends, from the calculations we have come to the conclusion that irrational number is equal to a rational number, which is never possible. So this is a wrong conclusion. Why? Because our assumption is wrong. That is, this number is not a rational number, and hence if it is not a rational number and if it is a real number, it must be an irrational number. Therefore, our assumption is wrong because it is leading to a false conclusion. Therefore, 4 minus 2 root 7 is an irrational number. Friends, similarly we can be asked another question like, to prove under root 5 plus under root 7 is an irrational number. We know that under root 5 and under root 7 to prove under root 5 plus under root 7 is an irrational number. Friends, we have proved previously in the first question that under root 7 is irrational number. But here we need the sum of two irrational number, because we can also proceed similarly as in the case of under root 7, and we can conclude that under root 5 is also an irrational number. But here we need sum of these two irrational numbers, and to prove that this sum is also an irrational number. Friends, in the proof part, let us first assume again the opposite of this statement. That is, this number is irrational. Therefore, under root 5 plus under root 7 can be expressed as p by q, where p and q are integers having no common factors and q is not equal to 0. Friends, if we proceed with the steps that we have discussed in the previous question, then if we make LHS only under root 7, we will get in RHS this value. And if we make here root 5, we will get here root 7. So, it will not solve our problem, that is, this complete number cannot be proved to be irrational. So, let us first square the equation 1. We will get under root 5 plus under root 7 whole square equals p by q whole square. That is, under root 5 square plus under root 7 square plus 2 under root 5 under root 7 equals p square by k square, which will give us 5 plus 7, that is 12, plus 2 under root 35 equals p square by q square, which will further give us under root 35 into 2 equals p square by q square minus 12, or under root 35 equals p square by q square by 2 minus 12 by 2, which will be 6. Now clearly, p by q, since we have assumed it as a rational, so its square will also be a rational, and divide by 2 will also be a rational. So this term is a rational term, this term is also a rational term, therefore this complete simplification will also give us a rational number. But under root 35 is an irrational number, because we don't know any integer whose square is 35. 5 square is 25, 6 square is 36. In between these two integers, 5 and 6, we don't have any integer between 5 and 6, so 35 lies between these two integers, and hence no number whose square is 35, so this under root 35 will not bear an integer. Thus, again a wrong conclusion, that is irrational equal to a rational number. A wrong conclusion. Why? Because our assumption, that is this assumption, is wrong. That is, root 2 plus root 5 plus root 7 is not a rational number. So if it is not a rational number, then if it is real, then it must be an irrational number, and hence the given statement has been proved. That is, conclusion is false because assumption is false. Therefore, the converse or the opposite of our assumption, that is under root 5 plus under root 7, is an irrational number, is true, hence proved. So friends, these were some questions, some examples on how to prove the irrationality of the given numbers, of the given irrational numbers. Thanks friends for visiting edupediaword.com.